So in today's video we shall talk about perfectly elastic collisions in one dimension. We have already seen what a perfectly elastic collision is in the last video. So today we are going to discuss a particular type of perfectly elastic collision which happens along one single direction, one dimensional perfectly elastic collision, which is also called a head-on collision. All collisions which happen along one single direction, which means that the bodies after collision move in the same direction in which they were initially moving. Such a collision is called a head-on collision. Okay. So we will today be discussing the mathematics associated with this collision, and we will derive some results, and then we will see some examples based upon that. So first thing is, if these two bodies initially they have to collide, this mass m1 which is moving with u1 and the mass m2 which is moving with u2, we understand that u1 must be greater than u2 for the two bodies to collide. Mass m1 must approach m2, right, for the collision to take place. Next is, we all know that when the collision takes place, the two bodies exert impact forces on each other, which by Newton's third law are equal and opposite in direction. And if we consider both the colliding bodies as one single system, then there is no external force acting on the system, and we can use the law of conservation of momentum, which in this particular case will be nothing but the initial momentum m1 u1 plus m2 u2 is equal to the final momentum m1 v1 plus m2 v2, right? Let us number this equation. Let's call it equation number 1. We shall be using it later on. Also, we have already seen in the last video that for a perfectly elastic collision, the total kinetic energy of the system also remains conserved, right? So by conservation of energy, then what do we get? We get half m1 u1 squared plus half m2 u2 squared is equal to half m1 v1 squared plus half m2 v2 squared. So this then becomes our second equation, which we can use along with the first equation to get the final values of velocities of the two colliding bodies. v1 and v2 we can obtain if we know the masses of the two bodies and their initial velocities u1 and u2. How do we get that? Today we are going to do the mathematics associated with this. So we first start with the equation number 1, the conservation of momentum equation, and we just modify this equation slightly. So what we do here is, we take this term on the left side and take this term on the right hand side. So what do we get while we do that? m1 u1 minus m1 v1 is equal to m2 v2 minus m2 u2. See that we can take m1 common on the left hand side to get u1 minus v1 is equal to m2 taken common on the right hand side will give us v2 minus u2, right? Let's number this as well, equation number 3 let's call it. And also from the equation for conservation of energy, see that we can do the same thing. v1 term we can take on the left hand side, u2 term we can take on the other side to get half m1 u1 squared minus half m1 v1 squared is equal to half m2 v2 squared minus half m2 u2 squared. And now once again let's take m1 and m2 common on both the sides. Half the term, half will cancel out throughout, the factor of half, and we'll get m1 into u1 squared minus v1 squared is equal to m2 into v2 squared minus u2 squared. Call it equation number 4. Now what we do is, we do equation 4 divided by equation 3. See that this term is u1 squared minus v1 squared, which can be written as u1 minus v1 into u1 plus v1. So when we divide this term over this, the factor of u1 minus v1 will cancel out, m1 will also cancel out, and we will be left with just u1 plus v1 on the left hand side. Similarly on the right hand side we will be left with v2 plus u2, right? From here we can rewrite this equation as u1 minus u2 is equal to v2 minus v1. This is an important relation that we have obtained. What is this relation? Let's call it equation number 5. See that u1 minus u2 is nothing but the relative velocity of mass 1 with respect to the mass 2 before collision, which we have defined in the previous video. We call it the velocity of approach of the two bodies before collision, velocity of approach. Whereas the other term on the right side of the equation, v2 minus v1, is actually the relative velocity of the second mass m2 with respect to the first mass after collision, right, which we have once again defined in the last class as the velocity of separation after collision. This is the velocity of separation. So, what are we getting here? Do we see that what we are getting, velocity of approach is equal to velocity of separation, and we connected these two values with the coefficient of restitution E. Remember, in the last video we defined coefficient of restitution as the velocity of separation after collision divided by the velocity of approach before collision, which in case of a perfectly elastic collision is coming out to be 1, because the two terms are identical, they are same in magnitude. So, we understand that for a perfectly elastic collision, the E value is 1. We just mentioned this fact in the last video. This time we have proved it, right? For a perfectly elastic collision, E is always 1. Now, we are not yet over, because we are yet to find out the values of V1 as well as V2, final values of that. So, to do that, what we do now is, instead of using the conservation of energy equation, which is an equation in squares of V1 and V2, which will be more complex to work with, we use the first equation, the conservation of momentum equation, and the fifth equation, the equation that we have just now obtained corresponding to velocity of separation and velocity of approach. We use equation number 1 and 5 to get the values of V1 and V2. How do we solve 1 and 5 together? What we do is, we multiply equation number 5 with any of the masses m1 or m2. Let's first multiply it with m2, and then from there we subtract the equation number 1, the conservation of momentum equation, and let's see what we get. Okay, so I'll just write the two equations here once again. The first equation is m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2, and the fifth equation that we have obtained is u1 minus u2 is equal to v2 minus v1. So, what we are going to do is, we first take equation number 5, multiply it with m2, and from that we subtract equation number 1 and see what do we get. So, do we see that when we multiply this with m2, we will have m2 into u1 minus u2, subtracted from that the left hand side of equation number 1, which is m1 u1 plus m2 u2. This becomes the left hand side of our expression. On the right hand side, on the same lines, we will have m2 into v2 minus v1, and subtracted from that m1 v1 plus m2 v2. See that a couple of terms will cancel out here. This plus m2 v2 and this minus m2 v2 will cancel out. And on the left hand side now, we can take terms together. So, what we have here is, we have m2 u1 minus m2 u2. So, we can take, okay, there is a minus m2 u2 here also. So, 2 times m2 u2 is there, and along with that, in the other terms, we can take u1 common in these two terms, this one and this one, u1 common, and inside the bracket we will be left with m2 minus m1, m2 minus m1. Whereas, along with that, we have minus of 2 times m2 u2. This is equal to, on the right hand side, see carefully, we are getting minus m2 v1 and minus m1 v1. So, we will have minus v1 taken common, and inside m2 plus m1. Okay, so, this is what we are getting. Let us solve this equation for the value of v1. We can cancel out the minus sign throughout here. So, this minus goes with this minus, and this term will become m1 minus m2 rather, by taking a minus common. So, that we will get the value of v1 from here as v1 is equal to m1 minus m2 over m1 plus m2 times u1. If you have any confusion here, maybe you can do this exercise separately on a sheet of paper. You can just check this, that this is what we will get after solving, plus the second term will be twice of m2 u2 divided by m1 plus m2. This is the expression that we will get for the final velocity of the first particle, the first mass m1. Okay. See that v1 is a function of both u1 as well as u2, and the mass is m1 and m2, right. So, substituting the values of m1, m2, u1 and u2 on the right hand side, we will be able to get the equation or the value for v1, the final velocity of the first mass. Now, similarly, what we can do is we can take the fifth equation, multiply it with m1 instead, and then add to that equation number 1. When we do that and we do this whole exercise on the same lines as we have done above, we will get the final relation for v2, which will be similar to the relation for v1, which will be m2 minus m1 by m1 plus m2 times u2 this time plus twice of m1 u1 by m1 plus m2. See that the two relations are symmetric. If we know one relation, we can easily write the second one, right? So, these are the relations for the final velocities of bodies undergoing perfectly elastic collisions. Okay. Now, using these results, we are going to derive a few special cases. There are some special cases that we study here in perfectly elastic collision, which we then directly use in the questions, the results that we get out of these special cases. So, the very first special case that we have is when the collision happens, when elastic collision happens between two identical bodies. That means m1 is equal to m2. Collision happens between two identical bodies. The masses of the two colliding bodies is the same. Okay. See from these two above relations, when we put m1 is equal to m2 in these relations, what do we get? Do you see that this term m1 minus m2 will go to 0? The second term here also will go to 0, and here if we consider both m1 and m2 to be equal to m, then see that this second term will be 2m by 2m, which will be 1. Here also 2m by 2m, which will be 1. So, we will be just left with v1 is equal to u2, and in the second equation v2 is equal to u1. Let us understand these results carefully. What is v1? v1 is the final velocity of the first body, whereas u2 is the initial velocity of the second body. Similarly, v2 is the final velocity of the second body and u1 is the initial velocity of the first body. So, what are we getting from here? From these results, we understand that this implies that the two bodies, the two colliding bodies, if they are identical, they interchange their velocities. The first body acquires the velocity of the second body and vice versa, right? So, the velocities of the two bodies get interchanged. A very important result, we use it directly into questions. So, if just to take an example, let us say we have two identical balls, each of mass m. One is moving with a speed u, whereas the other is at rest. This is simply at rest. After the collision, what do we expect? After the collision, this ball will come at rest, and the second ball, which was initially at rest, will start moving with the velocity of the first ball, so u. Okay, this is a very simple example of what really happens when two identical bodies collide perfectly elastically. Second special case is when a very heavy body hits a light body from behind. So, we have a heavy body of mass m1 hitting a very light body from behind m2. So, the condition here is that m1 is much greater than m2. This is the condition. Now, if we use this condition in the above expressions that we have got for v1 and v2, these two expressions, see that the value of m1 minus m2 over m1 plus m2, if we substitute m1 much greater than m2 over here, what do we get? m1 much greater than m2 would mean that m2 is negligible in comparison to m1. So, the numerator will be almost equal to m1. The denominator also will be almost equal to m1, because once again we can neglect m2 in comparison to m1. So, that this fraction will be almost equal to 1, right. Similarly, the other terms that we have in the above relation, let us check those as well. 2 times m1 over m1 plus m2. What do you think will happen to this relation? m1 is much greater than m2. So, here we can neglect this m2 in comparison to m1. So, that we will have 2 m1 by m1, which will be nearly equal to 2, right. and we have another term above in the relation which is 2 times m2 over m1 plus m2. What will happen to this relation? Because m2 is very small in comparison to m1, this expression would be a very small quantity m2 divided by a very large quantity m1, which will be almost equal to 0. So, once we know these approximated values now under the assumption that m1 is much greater than m2, we can use these values in the above relations for v1 and v2. When we do that, see that the first term will become, this is almost 1, so this is u1, right, whereas this term is 0. Whereas in the second term, we will have this term will be minus 1, m2 minus m1 by m1 plus m2 will be minus 1, and this term here is 2, right. So, when we do that, we shall get the final expression for v1 will be nearly equal to u1, whereas v2 will be 2 times u1 minus u2. These are the final results that we shall get for this particular special case. Now, let us observe what is the meaning of these results. The meaning of these results is that the first body, the heavy body, this will continue to move with the same speed with which it was earlier moving. v1 is nearly equal to u1. So, for example, let us say it is a heavy truck which comes and hits a bicycle from behind, right. The heavy truck which was moving with the speed u1 will continue to move with the same speed. It will not undergo any change in its state. Whereas, what will happen to the bicycle here, this relation, if we, let us say for the sake of understanding this, if we assume that let us say the bicycle was initially at rest, u2 is 0, it was standing on the roadside and the truck came from behind and hit it. So, if the bicycle initially was at rest, do we understand in this case what we get is v2 is equal to twice of u1, which means that the truck as it hits the bicycle will move with twice the velocity of the truck in the forward direction, right. So, this is what this result is about. The third special case that we can take up here is when a light body comes and hits a heavy body from behind. So, very light body, a bicycle this time hits a truck from behind. Okay. So, m1 which is now much less than m2. Under this scenario, let us once again see what will be the approximate values of the expressions that we have. So, m1 minus m2 over m1 plus m2. What do you think this will become now? m1 is much smaller, right. So, we can neglect it here as well as here. So, that minus m2 by m2 will be nearly equal to minus 1, right. Whereas, 2 times m1 by m1 plus m2 will be nearly equal to 0, because m1 is very small, and 2 times m2 by m1 plus m2 will be almost equal to 2, because now you can neglect this m1 and you will have 2 m2 by m2, which is nearly 2, right. So, under these assumptions now, when we substitute these values in the above relations, these are the values for v1 and v2 that we shall get. v1 will come out to be, which relations are we going to use? We are going to use these two relations here, the relations for the final velocities of the bodies moving with v1 and v2 are the final velocities of masses m1 and m2, right. So, when we substitute these assumed values over there, we will get v1 is equal to minus u1, you can check through the equations once on your own, plus twice of u2. This is the value of the final velocity of the first body, whereas the final velocity of the second body comes nearly u2 itself. Once again, let us understand these results as well here. What are we physically getting out of these results? So, these two results tell you that the lighter body, right, will move with a speed which is given by this, which we can understand maybe by taking u2 0. If u2 is 0 means if the heavier body is at rest initially. So, this body is at rest and the light body comes and hits this heavy body from behind. This would mean that the light body v1 will go with the same speed that it had u1, but in the opposite direction, minus u1, right? Whereas no change will happen in the velocity of the heavy body. It will continue to move with whatever velocity it is moving, because it's a very heavy body. So if a bicycle comes and hits a truck from behind, and let's say the truck is at rest, nothing will happen to the truck, it will still remain at rest, whereas the bicycle will now rebound backward and will move with the same speed with which it was coming initially towards the truck. Okay, this is also a standard case where we have a wall, a heavy wall, and a ball that comes and hits this wall with a certain velocity v. Ball being considered as the first mass, wall being considered as the second mass, wall being extremely heavy, and at rest, let's say, what happens is the ball rebounds with the speed v in the opposite direction, so that its final velocity is minus v. Okay, this is also a standard result that we use into our questions directly. Although in case your heavy body is moving, then you have to use this particular expression to find out the final velocities. So having understood all this, what we have done here is we have first discussed a perfectly elastic collision, the equations related to that, solved them to understand that the value of E is 1 for a perfectly elastic collision, then solving the equations further to get the final velocity equations for the particles, and then discussing 3 special cases. In case the two colliding bodies are identical, the bodies interchange their velocities after collision. In case a heavy body comes and hits a light body, these are the final velocities of the two bodies, and in case a light body comes and hits a heavy body, these are the final velocities. In both the case, understand that the heavy body will continue to move with its original speed. No change will happen in the speed of the heavy body. Let's take up a few simple examples now to understand how we use all these results in questions. So a very simple example first could be a question where we have two masses, let's say identical masses m and m each, both moving towards each other. The first mass is moving with 2 meters per second, whereas the second mass is moving with 4 meters per second. We are just supposed to find out the final velocities of the two balls, assuming the collision between them being perfectly elastic. So can we simply say that since the two colliding balls are of same mass, they are identical bodies, they will simply interchange their velocities. So the ball 1 will acquire the velocity of the ball 2, it will move with 4 meters per second towards left, whereas the ball 2 will acquire the velocity of the ball 1, it will move with 2 meters per second towards right. So this will be the final state of the two balls soon after collision. Okay. Let's take up another example now. The next example is 3 balls A, B and C. So let's say this is ball A, this is ball B and this is ball C. So 3 balls A, B and C of same mass m are placed on a frictionless horizontal floor. So they are kept on a perfectly smooth surface, so no force of friction from anywhere, and they are kept in a straight line. Ball A is moved with velocity u towards the ball B. If all the collisions are elastic, find out the final velocities of all the balls. Okay, so do we see what will happen here? If ball A goes and hits the ball B, what will be that will be the first collision, right? Ball A will acquire the state of the ball B, which means that the ball A will come at rest, whereas the ball B will acquire the state of the ball A, that means the ball B will start moving towards right with the speed u. This is what will happen after the first collision that takes place between the balls A and B. Now B approaches the ball C, right? The ball C which is kept over here, this is being approached by ball B now. So the second collision that takes place, that will be like the ball A stays in its own position, original position. B hits the ball C now, right? And since it is once again a perfectly elastic collision, the two balls interchange each other's state. So ball B will again come at rest, V will become 0, that's the C's velocity, and C will acquire B's velocity, that means C will start moving towards right with a velocity u. So can we say the final velocities of all the balls will be such that the ball A is finally at rest, the ball B is also finally at rest, whereas the ball C moves towards right with a velocity of u, right? So again we are directly using the results that we have obtained already. Let's take another example. The third example is a ball is moving with a velocity of 2 meters per second. This is a ball which is moving with 2 meters per second towards a heavy wall. This is the wall, let's say, and it's a heavy wall, so we don't need to know the mass here, we just need to know that it's a heavy one which is moving towards the ball at 1 meters per second. So the wall is also moving here, it's not at rest, it is moving with 1 meters per second towards left. Assuming the collision to be perfectly elastic, find the velocity of the ball immediately after the collision. So velocity of the ball, final velocity is what we are supposed to find out. So do we see this is a case of a light body going and hitting a heavy body, right? So can we use the result that we have just now derived for a light body hitting a heavy body? Which one? This one, right? We know what will happen to the final velocities of the two, right? So we use this directly over here. Can we say the ball will continue to move with the same speed of 1 meters per second, no change will happen in the velocity of the ball, whereas for the ball, let's call this as the velocity, the mass 1 and this is mass 2, so that the final velocity of the ball is velocity 1, which by definition is minus u1 plus 2 times u2. This is the expression that we have obtained above in the final result. So all we need to do now is substitute the values. What is u1? The initial velocity of the ball, which is 2 meters per second to the right. So rightward velocity, if we take as positive, then minus of 2 plus 2 times the velocity of the wall initially. See that the wall is moving with 1 meters per second but towards left. If we are taking rightward direction positive, that means the initial velocity of the wall here is minus 1, taking direction into consideration, right? So now we can solve this to get the value of v1 as minus 2, which is minus 4 meters per second. What do we mean by the value being negative? The value being negative means the ball moves towards left with a final velocity of 4 meters per second, right? So this is our final answer. So just to let you know, if we sometimes do not remember this expression, what do we do then? We can go back to our basic definition of a perfectly elastic collision and use that definition to solve this question as well. So there is another way in which you can approach the same problem if you don't remember the formula. What is that? Using the fact that the E value, the coefficient of restitution for a perfectly elastic collision is 1, which in the case of ball and wall here, we can define the same way as we defined E, v2 minus v1, the velocity of separation after collision, by u1 minus u2, the velocity of approach before collision, and substitute their values along with the correct sign. This is important. So understand that v2 here is the final velocity of the wall, v1 is the final velocity of the ball, u1 is the initial velocity of the ball, and the u2 is the initial velocity of the wall, right? So see that u1 is 2 meters per second, that of the ball, whereas u2 is minus 1 meter per second of the wall. And we also know that the final velocity of the wall v2 is also minus 1. The wall does not change its state, so it continues to move with the same velocity. Can we substitute all these values in the relation down here and get the value of v1? So v2, which is minus 1 minus v1 divided by u1, which is 2, minus u2, which is minus 1. Solve this to get 2 plus 1 is equal to minus 1 minus v1, and when we solve this for v1, we will get the value of v1 as minus 4 meters per second, which once again gives us the value of velocity of the ball along with its direction, along with the sign. Minus 4 means the ball is moving towards left, right? So we are getting all the answers along with the proper sign, that means along with the proper direction. Let's take up one more example. The next example is 2 blocks A and B, each of mass m. So this is A, let's say, and there is another block B over here. Both are having masses m each. So blocks A and B, each of mass m, are connected by a massless spring of natural length L and spring constant K. The blocks are initially resting on a smooth horizontal floor, okay, with the spring at its natural length initially. A third identical block C over here, okay, moves on the floor with a speed V along the line joining A and B and collides elastically with A. Then find the maximum compression produced in the spring in the process. Okay, so the figure is here in front of you. All the three masses are identical and the collision that takes place between C and A is perfectly elastic. When that collision takes place, understand that A will acquire a certain velocity and it will start moving, and we are supposed to find out the maximum compression that the spring will have under that state. So, let us first consider the collision that happens between C and A. Can we say as C moves and collides with A, initially there is no force acting on C and A both. The spring is in its natural length, so the spring is also not exerting any force. So, if we consider A and C as a system of two colliding bodies being identical in masses, can we say they will interchange their velocities? So, soon after collision what will happen? C will come at rest, whereas A will acquire the velocity of C, which is V towards right. So, A will start moving towards right with a velocity V, and what will happen as a result of that? Do we understand that A will start pressing the spring? It will start compressing the spring, as a result of which the spring will create a restoring force on both the bodies in the opposite directions, kx each, right? This kx force will accelerate the block B towards right, whereas it will deaccelerate the block A towards left, so that the block B will continue to acquire velocity which increases in time, and A, which already had an initial velocity of V, its velocity will start decreasing with time. Now, understand that the spring will continue to get compressed till the time A is moving faster than B, right? So, the moment when the velocity of A and B will become equal to each other, the spring will be in its maximum compression state. This particular aspect we have discussed in the previous video also. The same thing we are using here. We are saying that at maximum compression of the spring, velocity of A will become equal to the velocity of B at that instant, right? Now, can we find out that velocity? Can we say that if we assume this velocity is some V dash, then knowing that this system of two blocks A and B, which is moving under the effect of only the internal forces, the spring force, there is no external force acting on the system, which means that the total momentum of the system at any point in time will be conserved, right? So, can we say by conservation of momentum, the initial momentum of the system, which was only due to the velocity acquired by the block A, which is mv, can we say this will be equal to the momentum of the system when both the blocks are moving together will be both the blocks having same mass m plus m times they are moving with a velocity v dash. So, can we say this will be the final momentum of the system, the state at the state of maximum compression? So, from here we get the value of v dash as v by 2. Once we get this value of v by 2, now we go one step further and say that since the only force acting here in this system is a spring force, and spring force is a conservative force, we can conserve the total energy of this system at any point in time, and by doing that we can get the compression of the spring now. So, by using conservation of energy between the initial state means the state when the block A acquired a velocity of v, the spring was in its natural length at that time and the block B was at rest. So, can we say initially the only energy with this system was the kinetic energy of the block A, which was half mv squared. Finally, in the maximum compression state of the spring, both the blocks are moving with the same velocity v dash, whose value we know now. So, can we say the kinetic energy that the two blocks will have at that time will be half m into v dash square, which I can write as v by 2 whole square. This is the kinetic energy of the two blocks, plus there is some potential energy now stored in the spring, which will be corresponding to the maximum compression of the spring. So, half k x max squared, the potential energy of the spring due to maximum compression. Do you see we can easily find out the value of x from here now? solving it in terms of all the other known quantities. So see that the factor of half will cancel out throughout, and we can write this as mv squared is equal to 2m into v squared by 4 will be mv squared by 2 plus k into x squared. X we are supposed to find out. So this is giving us kx squared is equal to mv squared by 2 after solving, which gives us x is equal to square root of mv squared by 2k, right? This, or maybe you can take v out and say that this will be v into m by 2k. So see how we are connecting things together. We first used the results of elastic collision and then used further mechanics, conservation of momentum, conservation of energy, to deal with complex multiple conceptual questions. Okay. In the next class, we shall see similar questions and more such concepts related to collisions which are not perfectly elastic, maybe which are partially elastic or perfectly inelastic. We shall deal with that in the next video.